Greetings, welcome back to the course on biomedical ultrasound, fundamentals of imaging and micro machine transducers. My name is Srinivas Bhaskara, TA of this course. Today let us look at how thermal oxidation happens, mathematical modeling related to that, especially Deal-Grove modeling, and see different aspects empirically. Okay. So, let us look at the slide. So, if you look at it, we have dry oxidation and we have a wet oxidation, and why the name came like dry and wet, it is very obvious. You are only using oxygen here for oxidizing the silicon. Here you are using water vapor, right, for oxidizing the silicon. So, if you look at dry and wet oxidation, I want you to be very clear with the terminology. So, we have you have oxide, right. So, you have oxide can be either grown or deposited, right. So, if you look at the growth, if you look at, let us say, grown oxide or deposited oxide, what is the difference between those two? Now, here in the grown, if when somebody says grown oxide, you have a silicon as a precursor already available. Okay. This is like a wafer is already there, silicon wafer is already there. You are just supplying oxygen or water molecule, and it will result in silicon dioxide. Of course, extra remaining gases and all will be there. So, here the precursor is already a wafer, right. When I say deposited, right, now precursor silicon and oxygen both are precursors. They will try to react on the surface and then form silicon dioxide, correct. So, if you have a silicon wafer and grow it on top of it, that will become silicon grown oxide, like fruits grows on the tree, right, something like that. Okay. Now, deposition is the other way around. Okay. So, now here whatever we are discussing in this lecture is only related to the grown oxide, right. We are not discussing about deposited oxide. There are a lot of things to discuss in the deposition as well, right. So, now let me erase this ink, right. So, let us get back to the dry and wet oxidation. We are talking about only grown oxides, right. So, silicon oxygen, it will become dry oxidation, then silicon with when it reacts with the water molecules, right, it will become silicon dioxide, and extra H2 will be released, and that will be that will come out of that reaction, right. So, one is wet reaction, one is dry reaction. Now, if you look at it, the process temperature is around 900 to 1200 degrees centigrade, and wet oxidation is 10 times faster than dry oxidation. This we will see mathematically later. Just right now you look at it as just a statement, we will prove it later on. So, if you look at this process temperature, it is around 900 to 1200 degrees centigrade, right. Do we really need these high temperatures? Now, I do not know how many of you have observed it. Suppose if you have a silicon, if you expose it to the atmosphere at room temperature, right. So, in our labs we have lot of silicon wafers. When we expose it to them, right, there will be very thin oxide, okay, very thin layer. This is from the top view. Side view, if you look at it, let us say silicon, I have 300 micron thick silicon. There will be a very thin, let me change the color, there will be a very thin layer of silicon dioxide that is formed after a few months. And if you look at the thickness of this silicon dioxide that is formed is in the order of nanometers. Okay. This is native oxide grown. Okay. See what happens, why that oxide is growing. I am not interested in the oxidation, but because in the atmosphere there is oxygen and water vapor, right. If there is a humidity or something, right, there is a reaction that takes place and silicon dioxide is formed, even though you are not interested to form the silicon dioxide. So that silicon dioxide is on the order of very few nanometers, and the quality of that silicon dioxide is not very good, right. Now why we need to have very high temperatures, that we will see through a problem. The thing is, here I want to just give a hint. If you can enable, like this is concept of diffusion, right. So some of you might be familiar, this diffusion constant, if you look at it, is around d to e power minus Eg by kT. Now if the temperature is more, right, obviously this term will be less and then the diffusion is more. Are you getting it? So at higher temperatures you will have higher diffusion, and that higher diffusion results in the thickness, and how they are connected, that is what our central focus of this lecture is, right. Now this dry oxidation is an excellent insulator, right, and you might have seen in the MOS transistors, right, you have something like this, right. So gate, this is not the gate, this is drain, and this is source, and of course vice versa, one can do anything, okay, and there is a gate. Now this gate you will apply some voltage, right. So sorry, let me clear this, let me draw properly. So you have, let us say, source and you have a drain, right. So for application of the voltage, here you use very thin oxide, right. This is gate, of course there is metal contacts here, this is for source, this is for drain, right. Now this gate oxide has to be very good, right. So now one can guess, out of this dry oxidation and wet oxidation, what will be an excellent, which one give you excellent oxide material. So just think about it. So what gives is a dry oxidation, right, because you see only a silicon dioxide is getting formed. Here what happens is, along with silicon dioxide there is another guy here, right, hydrogen, correct. Now what happens with this guy is, now it has to be, see it is in gaseous form, it has to leave that particular reaction from there and then go out, right. Now what happens is, it will create holes in the oxide films that are formed and then leave. Because of that, the material property will be compromised compared to the dry oxidation. But dry oxidation is very slow, okay. So partially I can give a hint, okay. Think about the diffusion constant of oxygen and water vapor, that will give you the answer, right. Now anyways, we will see, look at the equations and then talk one by one, right. Now this is generally used for in gate oxides, right. Now wet oxidation, and there are plenty of examples where you need a wet oxidation, where we can use it for film oxide, masking oxide, and this is quality we discussed already, diffusion of hydrogen gas out of the film, which creates path for the electron can flow, right. Now this we have also discussed, like room temperature silicon creates native oxide, very thin, and it is not good, okay. So compared to this dry oxidation 1 nanometer, you compare with this 1 nanometer native oxide, it is room temperature native oxide is very bad, because the point here is you are doing at very high temperatures, right. High temperatures plays a major role for the crystal to form clearly, right. Now one more question here is, let us say for example I have 100 micron thick silicon wafer, upon which my idea is to grow 100 just for let us say, just to keep the numbers very clear, okay, let me take another number. Okay. I do not want to confuse you guys, it is a very simple topic to deal with. Right. So, you have 500 micron thick, this is a cross section that I am drawing, right. So, you want to grow 100 micron thick silicon dioxide. Right. So, what do you think? Suppose if you think that you have grown 100 micron, is it going to grow on top of this 500? Is it going to grow like this on top of this? So, the overall stack thickness is around 600 micron. What do you think? It turns out it does not happen like that. Okay. It turns out that, right, you do not get additional 100, but what happens is in the process, right, some part of the silicon is consumed and some part will be grown on top, right. So, how much is consumed, right, is like, if you know entire thickness is, let us say silicon dioxide thickness is x, right. So, what you can think of is 0.46 x, right, of silicon is consumed and 0.54 x, right, extra layer is formed. So, according to this, according to our calculation, let us say we are expecting 100 micron, in that 46 micron is consumed in the, I mean 0.6 micron thick of silicon is consumed and 54 micron thick silicon dioxide is formed on top of this 500. So, overall if you look at the measurement, right. So, you have 500 plus 54 micron. So, overall you will have 554 micron thick silicon, I mean thick stack layer, right, instead of 600, right. Now, this is very important okay, for your exams as well, okay, assignments or whatever. Okay. Now, how that is formed, why, like, you know, how you want to, how can we say it is 0.45 and 0.46, we have some calculations here, right. So, if you look at it, right, now thickness of silicon dioxide, if you relate to the density and all that stuff, so finally the number comes out to be 0.46, right. So, let us move on to the next part, right. Now, how does the oxidation happens, right. So, you have a furnace, okay. So, this furnace is made of quartz, so as to withstand very, very high temperatures, right, and you look at this one, right, there is a boat here, right, upon which the wafers are stacked, okay. So, you have a boat upon which the wafers are stacked like this. So, you can do the oxidation with many number of wafers at a time, right, depending on what is the length of this furnace, right, the chamber, whatever. The chamber is made of this quartz, right, and you look at this, this very quite evident, you need oxygen for dry oxidation, and of course, we can't do directly there. So, how we can do, we like there is something called RTP, right, you can't increase the temperature directly to you know to 1200 or 1900 something. So, you slowly increase the temperature, right. So, meanwhile, to avoid the oxidation at lower temperatures, one can use nitrogen, then one can purge the oxygen slowly inside, right. So, that is one way, right. This comes under dry oxidation. Now, what is wet oxidation? Now, you need oxygen, I mean you need a hydrogen, okay. It is a bubbler here, it is a bubbler, right. So, oxygen enters and creates the water vapor here, right, send it water vapor inside this chamber, and then this water vapor reacts with the silicon and then form that, and of course, the story is going to be the same, right. So, the temperatures is around 1900 to 1200 degrees centigrade. So, now if you increase the temperature, the diffusion is going to be more, right. So, what is that diffusion and all those things we will see very soon now, right. So, this is how the setup looks like. The atmospheres inside the furnace is around 1 atmosphere or something like that, right. So, not like a PVD and a sputter, okay. So, typically the pressures are very high, right. Now, some parts we have discussed already. If you look at the applications of thermally grown oxides, you can use it for field oxides, right. And if I come from the bottom, okay, let us go from bottom, right. So, these are now once you do something called chemical oxides from cleaning native oxide, what happens is there is something called piranha cleaning, okay, piranha cleaning, right. So, where the components are H2O2 and H2SO4, right, different ratios 1:2, 2:4 or something, whatever, right. So, here what happens is when you, this is called pre-cleaning step, okay, right. So, we have contamination protocols in place, one has to clean it properly. Now, once you clean it, because there are oxidizing agents that are involved, when you clean the silicon wafer, obviously you will have silicon dioxide, right. Now, this silicon dioxide, right, will be the silicon dioxide that is formed is in the order of nanometers, few nanometers, but if you look at the quality is not that great. So, what one has to do is, if they do not want to grow the silicon dioxide on top of this, what I can do is, once you complete the piranha, you can do HF dip, okay, for 30 seconds, which is very dilute, right, 1:50 ratio. You take water, water is 50 times, and then this is HF, okay, concentric HF, 1:50 ratio you take, and then you put after piranha, you dip the wafer in the HF solution, and you can remove the native oxide if one does not want to grow anything. Then gate oxides, tunneling oxides, right, and pad oxides. So, these are used for insulating devices from each other, okay, field oxides we have, and then masking oxide, right, maybe in the diffusion or ion implantation you need to have a mask, right. So, something what happens is like you have a silicon wafer, now you want to only work with this in this area. So, you do not want to expose these two areas, right. So, here you can mask it, right. So, then you do ion implantation, okay, then you can only work with this particular area, okay, these are shielded from that surface, right. So, that is about it. Then you can use deposited oxides and metal oxides, like insulator between the metals. So, mask, you see, this is very simple. Now, you let us say you have a silicon wafer, on top of this some metal is already there, right, let us say aluminum or something is there. Now, you want to grow silicon dioxide on top of this. Now, imagine if you expose this aluminum to 1200 degrees centigrade or 800 degrees centigrade, what will happen, right. This aluminum will diffuse into the silicon, correct, and spoil the properties of the silicon, correct. You do not want to do that, you do not want to expose it to high temperatures. So, what you do something called sputter, right. It is typically done at room temperature, and you will get a nice silicon dioxide coating. So, depending on contamination, right, like if there is a metal and you should not expose that particular wafer to high temperature processes, right. So, that is about it. Then how actually the oxidation takes place, how to mathematically model it, right. So, what we can do is, right, there is a accepted model, mathematical model for the oxidation called Deal-Grove model, right. So, we are going to see there are terms and conditions apply for any model sometimes the model may fail or something, but this is like kind of accepted across these thicknesses and then temperatures, right. Yeah, you know, this is like this model try to replicate what exactly happens in a real time scenario when the oxidation is taking place. So, let us go into that. So, for that let me put some things in perspective. So, let us say you have a silicon wafer, right. Now, this silicon wafer, this is a cross section I am drawing, right. This is the thickness, right. Now, on top of this silicon oxide grows, right. Okay, let me take another color. Right. So, initially what will happen? Initially there is no silicon dioxide, right. So, eraser. Initially there is no silicon dioxide. What you have is, see, this silicon wafer is kept inside a chamber like this. This is in a chamber and where there is lot of oxygen or water molecules available, lot of molecules are available. Now, they will first come to the interface and then they try to react and form very thin layer of silicon dioxide. So, what happens here is surface reaction, right. Now, you are maintaining this guy around 1200, 900 degrees to 1200 degrees centigrade, right. Now, the reaction will takes place with the energy that is available, thermal energy, right. Now what is the next step? What about the other guy, next set of oxygen or hydrogen or water molecules? What happens is they can't see the silicon, right, silicon is here. Now, what happens is they have to diffuse through this layer, this is what I was saying, diffuse. All right. Now, let us understand this mathematically, right. Now, what we will do, so I will just rotate this structure, sorry, I will just rotate this structure, right, to the left by 90 degree and then let us start discussing about that, right. So, now you have, okay, let me take the red pen. Okay. So, this is the thickness silicon just for our understanding purpose, okay, I am doing like this. Then there is a very thin layer of silicon dioxide is formed and this is the ambience. Here the ambience is in the furnace, right, it is inside the furnace, right. Now, here lot of oxygen or water molecules are there, they will come and see the surface and they will try to diffuse to this silicon interface, right. So, now let us say this is Cg concentration of that particular oxygen or hydrogen molecule, then here at the interface it can be Ci, right. So, what has to happen is to form next layers of silicon dioxide. So, this molecules has to diffuse, first part, diffuse through what? Through silicon dioxide layer, right. When somebody says diffuse, right, one has to ask this question, diffusion of what in what? Now, here in this case what is diffusing? what is diffusing is oxygen or water molecule in what? Silicon dioxide. So, one has to look at the data sheet of this guy, right. What is the diffusion of oxygen in silicon dioxide with respect to time, right. So, if I write diffusion constant, d is d naught e power something like E g by k t. This E g might be different for oxygen and there is water, right. So, the diffusions are different, right. So, now erase this part, right. So, when somebody says diffusion of what in what, right, just be with me, okay, it will be clear soon, right. So, you have ambience outside. Now oxygen or water molecules will reach the surface, then they will diffuse, and here there is something called surface reaction takes place. Right. Now, in the ambience there are lot of molecules, okay. You do not have any problem, you have infinite possible what do you call them, reactants, right. But the bottleneck here is it has to come to the surface and then it has to diffuse, right, and it has to react. So, if you try to model this, right, there are two kinds of flux that is happening. Inside the oxide there is one flux, right, do not worry about terminology, right, I am just using F1 and F2 something like that. So, the flux that is flowing inside, right, is let us say defined by F1, and there is a reaction that is happening, right. So, that flux is F2. Now, there is a flux outside as well. What is happening outside? Let us say for example, only oxygen is there. Oxygen is diffusing inside oxygen, right, that will be very very high, correct. So, you can ignore that flux, that is what I am saying. So, F1 and F2 you have two flux, one is diffusion flux and reaction flux, right. So, how to model this diffusion flux? F1, right, is modeled by using Fick's law. What happens? Because there is a concentration gradient, right. So, Fick says that F1 flux is proportional to the concentration gradient, and F1 is minus d dou c by dou x, right. This is a diffusion constant, remember d depends on the temperature. At different temperatures different diffusion constants are there, okay. So, it is not a hard constant, right. So, now what is another one? This is we will get into the details. So, why minus is there? It is very evident, right. So, because this concentration, see the definitely what happens, like water flows from higher height to lower height, right, like something like this. So, water flow will be like this, right. So, this minus will counterbalance this concentration, because if I just calculate the concentration gradient here, it will be minus into minus it will become plus, right. So, just to counterbalance that, right. So, erase this part. So, what is the next flux? F2, which is corresponding to the surface reaction, is defined by Ks into Ci, okay. This is what is called as surface reaction coefficient, right. And again this Ks depends on different properties, material properties, right, and the orientation of the silicon, etc., etc. Now, you can see only the partial differential equation in terms of the lengths, right. Now, what about the time? So, this is a final equation, right, rate of change of silicon dioxide that is formed is F by Ni. This Ni is number of atoms that are incorporated, oxygen atoms that are incorporated in the silicon dioxide formation. This F is either F1 or F2. See, this F can be F1 or F2, right. See, why it is F1 or F2? Because in equilibrium these F1 and F2 should balance each other. Okay, imagine a scenario. Okay, let us say diffusion flux is more. What happens? Here the reaction is taking place, correct? More and more will accumulate here. What happens? Because of that, the concentration gradient will fall, right. The concentration gradient in compared to earlier, it is less, right. So, this F1 will fall to balance it out with the F2. The another argument is, if you have applied so much high temperature, if C1 is becoming 0, like because literally as soon as the atom comes or molecule comes, it is going to be like form a silicon dioxide. Now what happens? The concentration gradient will increase, this F1 will increase so high such that will balance with the F2. Finally, at equilibrium F1 will become F2, right. Now you have a differential equation in terms of the length and with respect to time, correct. Now if I can solve these three, put these three together and then solve it, right, I can find out what is the x. Question mark is what is the thickness with respect to these coefficient d, k, s, and finally you need to find out how much is the thickness that is formed if you run the deposition or oxidation for some time, correct. So we have established the necessary conditions to find out what is the thickness of silicon dioxide that is formed, and we will continue the Deal-Grove modeling in the next lecture, and we will see some problems relating to the same. Thank you.